If you make products with moving parts, here's a great new application that will help you answer two questions. First, what will the product look like when it's moving? And what are the kinematic properties such as distances, accelerations, and interferences? Let's analyze this free body sketch of a suspension in Animation Designer. Watch as we quickly define the motion between components using mechanical joints that simulate real-world conditions. A fixed joint locks down what components shouldn't move, such as the suspension and frame, and a revolute joint will allow the wishbone to pivot about the frame. Notice the minimum number of inputs. We only have to define the joint, but other operations such as rigid group creation are done automatically. Rigid groups tell the system what can move but are being created during joint definition. This automated approach is perfect when defining the motion of a small assembly. A spherical joint will simulate how the wheel pivots around the wishbone, and to simulate a bumpy road, we'll slide the curve back and forth. Finally, we'll connect the road to the wheel. Let's check our progress by running the animation. A fast solver in Animation Designer gives results instantly so you can try different scenarios in less time. Now let's automate motion by moving the ground. Let's add a motor that will slide the road back and forth. We'll add an event to move the road in one direction, then another event to reverse that direction, and a final event returning the road to its initial condition. You can have as many motors as needed simulating very complex operations. Once complete, motion is transferred through the suspension components, causing it to move up and down. The behavior looks correct, but if any changes were needed, we would simply access modeling and modify the sketch. Now we can determine the shock travel by adding a measurement between parts. You can add linear or angular measurements that report displacements during the animation. A built-in graphing function will report the measurements so you can visually see critical characteristics such as maximums, minimums, and points of inflection. Within a few minutes, we have identified the travel required for the shock absorber. Animation Designer in NX12 is a perfect fit for designers that need to see their products in action and understand kinematic properties such as distances, velocities, and accelerations. In this next motion simulation example, we'll see how parts can actually push others around, creating a very realistic simulation. The goals are to create a simulation that this crank arm actually rotates and pushes the small pin, which in turn pushes all of these parts so they all work together. The command that we're going to be using here is contact face, and it doesn't allow interferences. It actually allows contact and pushes things around. So we'll begin by locking everything down. Standard fixed joint on the large component and the small pin, and then some slider component joints to allow the parts to slide back and forth along one another. And one more slider joint on the small blue part, and that's going to allow the mechanism to act very freely as it's sliding back and forth. And last but not least, we need a rotational joint to go around this sort of pin. And we'll just simply make this go around the axis, and the default point will be automatically picked for us. Now that that's complete, we don't have any contact faces yet. Let's check our progress. So we're going to go to our display color, and we can quickly verify that we have all of our rigid groups created for us. Now remember, the joint command automatically will create the rigid groups for us. In a few demonstrations, we'll see how to create rigid groups manually. But for now, this automated approach works great on small assemblies. Now let's go ahead and add some position motors. So what we're going to do is we're going to take this rotational motor and we're going to simply rotate it 90 degrees. We'll insert another event and go back 90 degrees. Insert another event, have it return back to where it was. And then one more sort of panning this thing back and forth. We enter a minus 90 here. Once complete, we hit the play. We see how the crank arm goes back and forth. Now to change direction, it's just a simple matter of going to our revolute joint and reversing the direction. And that will get the crank arm to go in the opposite direction for us. Alright, now let's add the contact face operations. So the inputs are fairly simple. Just click the command, and we want to add a contact face to this interface, and we'll apply that. We'll add some contact faces to these small little tabs here. I'm going to pick a couple extra just to make sure that we get a good contact sort of surface area. And then one last contact face between these green faces on the very back of the model, the front of the model, and this small pin. And not last but not least, we'll get these small inside faces of this crank mechanism. All right, if you're wondering why I just don't pick the entire part, it's a performance thing. The contact face does require a small amount of calculation overhead, but as you can see with our fast solver, things happen in real time. And this is a pretty realistic assembly that we have here using contact faces. Normally what would happen is one face would bump into another and occupy the same space, creating an interference, which we can detect, but this particular contact face gives us a very realistic motion, all within inside of Animation Designer. In this motion simulation demonstration, we'll see how we can transfer motion from one part of a model to another. The operation that we're going to be using is called a coupler, and common types of couplers are gears, chains, belts, rack and pinions, and mechanical cams. The goal here is to have the blue sprocket turn the silver sprocket, which will turn the cam, which will make the lifter go up and down. So let's get started. First thing we're going to do is we're going to lock everything down with a fixed joint. And I'll lock these small axes down, or axles down, and the small guide pin for my lifter. And then we'll apply some rotational joints using a revolute joint around our blue sprocket and the axis. And I'm going to pick that cylinder to be my axis of rotation. One more revolute joint around this small component. But take note, as this pulley rotates, I want the cam to rotate as well. So I'll simply pick both of these to be my first set of objects to pick. Then the axis and the center of that axis. Again, just follow the inputs and notice the Q line at the very bottom of the screen if you get stuck. One last joint will be a slider joint to allow my lifter to go up and down. And that will pretty much define the motion required to get our cam mechanism to work. All right, let's check our progress. First, let's turn the display color on and make sure we have all of our rigid groups defined. Notice how we have the rigid group in dark blue. We have one for our sprocket, one for the other sprocket, and the lifter. Again, the joint command was creating the rigid groups for us automatically. So all I need to do is simply apply some joints, and to test them, let's go ahead and rotate our model around. Notice that one sprocket is turning, but not the other. So what we're going to do is add a coupler across them. What a coupler does is it transfers motion from one joint to another. So I'll pick my chain belt, and I simply pick my first sprocket, my second sprocket, or my revolute joint, I should say, and I'll enter in a sprocket ratio between the two. Then if I grab my rigid group command and I simply spin things around, we can see how we're now transferring motion across our model. One last coupler to add, and that is for our cam. Just simply follow the prompts. What is our cam joint, which is always going to be a revolute joint? What are the faces? What is my follower, which is always a sliding joint? Simply pick that joint. Notice it's the only one highlighted on the screen. And what are the faces? And I want the bottom faces of my lifter, so I'll simply use quick pick to select those faces on the very bottom. Once that's done, let's grab our rigid group, spin this around, and make sure I grab the right rigid group though. Spin this around, and notice how we're transferring motion across two joints and making our cam go, or our lifter go up and down. Very useful workflow. We'll add a speed motor this time, and we'll just give it a few hundred RPMs. Nothing fancy. And when we hit the play, notice how this is doing this motion for us automatically. Key operations here were the couplers that are all built into Animation Designer. What motion simulation demonstration would be complete without an engine? Here we have a single piston engine comprised of discrete components. One for a piston, connecting rod, crankshaft, and so on and so forth. This is also built with assembly constraints for mating, aligning, and so on and so forth. So if we grab our assembly move component command, we can actually see how this component is going to animate. So let's go ahead and move things around and see how our piston goes up and down. This is all because the assembly was built with motion in mind. Alright, so going to an animation is quite simple. All you need to do is activate Animation Designer and then go to something called the Joints from Assembly Constraints, and the system will automatically create all of your joints and rigid groups for you automatically. So now it's just a matter of going to your Move Rigid Group. We'll pick, say, the crankshaft, and we'll simply rotate it about maybe this axis, and you can see how things operate as you normally would expect. So basically, we looked at the assembly constraint definition, and we applied the appropriate joints to mimic that same assembly definition. Now, if we want to learn some kinematic behavior, it's quite simple. All we need to do is put maybe a speed motor on one of our joints, give it an RPM of maybe, I don't know, 50, something nice and simple, hit the play, and we can watch this thing go up and down. Now, if you're wondering what the piston travel is, it's just a matter of adding a measurement to the, say, the top of that piston, and we'll pick the top face of the piston, and then we will pick the top face of our cylinder, and we'll turn on a handy graphing function, and that will show us exactly what that travel is over time. And you can see how it's plotting it for us. Now, if you're wondering where that odd little bump is, that's because the piston is actually traveling past top dead center, or past the top of the cylinder, giving us that sort of inverted sine shape. But this is a great way of going from your assembly to animation literally in just a few clicks of a mouse and getting some valuable kinematic properties of this. Common question during the design of products with moving parts are, what will my product look like during normal operation, and are there any clearance violations when parts move? Siemens NX Animation Designer is a motion simulation application for analyzing kinematic behavior when the effects of forces are not yet needed. Let's start defining the motion of our assembly by first creating rigid groups to indicate what can move. We can select components directly or by rectangle select. Watch as we freely choose components without having to adhere to any assembly structure rules, giving us total flexibility and moving whatever we want. We can also choose complete subassemblies using the Assembly Navigator. This subtle yet important detail here is that you can move any component regardless of where it lives in the assembly structure. Notice how we'll move the small slider supports that are buried deep in some subassembly. To verify you have the right components in the right rigid group, let's change our display to show each of the rigid group in its own color. With this capability, you can instantly see what groups of components can move. Now that we have the rigid groups defined, let's define how they move relative to each other. Animation Designer includes the most common joints for fixing, sliding, rotating, and even moving components along curves. We'll fix the base and add a slider joint to allow the transport frame to move back and forth and side to side. The last joint will move the gripper up and down. Let's get a glimpse of how our motion definition is progressing. Just select a rigid group, move it around, and the model updates accordingly. There is no need to solve the model or wait for any position calculations to happen. That looks perfect. Now we're ready to add some motors and set the exact sequence of operations. The first motor will move the transport frame back and forth, the second will move it from side to side, and the last will move the gripper up and down. Each motor can have multiple events for adding dwell or return steps, and we'll see a simple way to create more events. These position motors are for intermittent motion, but we also have motors to provide continuous movement. We use a timeline control that provides video editing-like interaction. A quick mirror operation creates the return actuation of each motor. Now it's just a matter of defining when each event should occur. The goal here is to have the transport frame move to the right, then it needs to move out. Finally, the gripper needs to extend down to the conveyor so it can pick up a part. The last step is for the gripper to return so the part can be moved to the next operation. Motion in Animation Designer is time-based, so it's a simple drag of the time bars to specify the desired sequence. Watch as we drag the time bars around. Some useful tools are snapping to guarantee continuous operation. You can move an event, you can drag the start or end to alter the duration, you can mirror, and you can split an event to add a dwell. In just a few minutes, we were able to completely define the motion behavior for this machine. Animation Designer is perfect for designers who need to visualize products in motion and find collision between moving parts. Now that we have defined the correct sequence of operations, let's answer the question if there are any interferences between moving parts. Animation Designer includes interference checking that can show interfering parts during a motion study. Options are provided to stop an animation when a collision is first detected, and modes are available for fast or accurate checking. We'll get a better view by zooming in and using a timeline to determine when the collision occurs. So we can monitor the clearance during the entire range of motion, let's add a measurement between the faces of the slider and support. Once done, we can plot this measurement on a graph and look for any trends, maximum or minimum values. A handy probe tool within the graph dialog lets us dial in on the point of interference. We'll pan the timeline just past the initial point of interference so we can use both parts as a guide when we model away the problem area. Now it's just a matter of setting the support as the work part and using modeling tools to address the issue. We could address this fix in many ways, such as specifying a precise clearance between the slider and support, or make the support the exact length as the others. Let's keep things simple and just move the face out of the way to some arbitrary distance. We can rerun our animation keeping collision on and notice there is no more interference. But what about the clearance? Just turn the graph on and notice the distance between the faces is plotted. In just minutes using Animation Designer, we were able to find and fix a collision that ensures our design is ready for production.